when a forward reaction and a reverse reaction are occurring in a dynamic state, where we're looking at a forward and a reverse reaction being written with double arrows. The concept of equilibrium will be the topic of our next 3 chapters. You can see just by the devoted time, I'll get that out, the devoted time to the concept of equilibrium, we can see that it's quite a large and important concept. So we'll begin by looking at some very basic ideas first, and then taking a look at how we apply those in a mathematical situation. Reactions are reversible. Let's just make up a forward reaction where reactant A and reactant B go forward and to create 2 products. We'll just call C and D, just some generic chemistry. And looking at the reverse reaction, we can see that C and D go back indeed to form the original A's and B's. So a forward and a reverse reaction are occurring. Notice initially, and we would call that as time 0, we only have a forward reaction occurring simply because we have no product made at time 0. As time goes by, C and D begin to accumulate, and we can see that a reverse reaction begins to form, and it all goes back to what we called the collision theory. We must have molecules collide for bonds to break and new bonds to form. And if reactant A and B are the only things available to collide, well, we're only going to go in one direction. But as C and D begin to accumulate, the chances of their successful collisions also guarantees a reverse reaction. And eventually, the rates become equal. The forward and the reverse reaction reach an equilibrium state where you can see it's the flat line on our graph. I want you to jot this graph down in the little margin area. You're hearing my dog Sadie bark. Sadie. We have a XY axis as time is going by on the x-axis. We have the rate of reaction. That goes back to what our kinetics chapter talked about. In kinetics, a forward and reverse reaction over time develop an equilibrium. You can see, and I want you to label the forward reaction. The rate at the beginning there is quite fast in comparison to the reverse reaction. Of course, that starts at a 0, 0. There is no reverse reaction at time 0, but given enough time to accumulate more and more product, we start to see the reverse reaction take off. Notice that an eventual flat line is achieved, and that indeed is the state of equilibrium. So what is equal at equilibrium? Well, the rates are equal. Kinetics, how fast the reactions are occurring. But, very important, it does not mean that concentrations are equal. I'm saying that reactant A and B compared to product C and D don't have to have the same amount present. We might be creating far more product, or we might be creating far more reactant in comparison to one side of the arrow or another. The forward and the reverse reaction are occurring at the same rate, but not necessarily guaranteeing me the same amount of reactant and product. Rates are determined by a lot of different things. Concentrations, activation energy, the temperature, all kinds of things as we studied in our last chapter on kinetics. So that net concentrations do not change at equilibrium. It's a very powerful statement. Once equilibrium is achieved, the concentrations of reactants and products remain unchanged. That was the flat line if you glance back at your graph. So as time goes by, we achieve the same rate of forward and reverse reaction, where we reach an equilibrium state of the amount of product and reactants. This concept of equilibrium, let's just begin by thinking about that in terms of a big equal sign. Those double arrows, I have a hard time typing those in PowerPoint. A forward and reverse reaction typically are seen as a double arrow, one on top of the other going into the right and one heading to the left. Sometimes I'll just type a simple equal sign just because it's easier to type than to try to create a forward and a reverse arrow. But if we look at an equilibrium for dinitrogen tetraoxide, and it's in a gaseous form. I have a forward arrow and a reverse arrow. That's the best I can do for an equilibrium sign. And it goes on to form 2 molecules of nitrogen dioxide, so NO2. It's a balanced equation. Remembering kinetics, we assume that these are both elementary reactions. Now I'm going to take us back and stress what I've just said. In the very last section of our kinetics chapter, we talked about reaction mechanisms. And whenever we wrote a dynamic equilibrium with a forward and reverse reaction, one going forward, one going in reverse, those were always elementary reactions. They were a part of a multi-step mechanism. Every one of the equations we're studying in a concept called equilibrium are indeed elementary reactions. They may be part of an overall reaction mechanism, but each elementary reaction will be studied in terms of equilibrium. Consider that in terms of its kinetics. We get our rate laws directly from the elementary reactions. So when I'm looking at N2O4 in equilibrium with 2 units of NO2, I now know that there's a forward reaction with a K forward and a reverse reaction with a KR, we'll call it for reverse, where we can write a rate law from their equation. Now remember from last chapter, rate is equal to K times the concentration of the reactant raised to some power. If I think about what F is standing for by that K constant, it's standing for the forward reaction. Just automatic pilot from our kinetics chapter. If I'm looking at the forward reaction, the reactant is N2O4. Its coefficient is a 1. Write a rate law for that elementary reaction. We'd write that rate, and that little f is just showing you I'm referring to the forward reaction. Rate is equal to K times the concentration. Remember the brackets are molarity units. Concentration of molarity. So the bracket there, I would read that. Rate is equal to K times the concentration of N2O4 with respect to first order. Read the reverse reaction and jot down its elementary rate law. The rate of the reverse reaction is equal to its K constant times NO2 to the second order. That concentration of NO2 would be the second order based on the stoichiometry. Notice it has a coefficient of 2. And if it's an elementary equation, the rate law comes directly from the equation. At equilibrium, thus the term equilibrium, the rates are indeed equal. If the rates are equal, we can set up our rate law for the forward reaction directly equal to the rate law for the reverse reaction. Kf times the concentration of N2O4 to the first power, set equal to Kr times the concentration of NO2 to the second order. The forward and the reverse reactions are indeed at equal rates. What I'm going to do now is rearrange this ratio to get the K constants by themselves. So what I'm hoping to do, if I think about what we just had, Kf set equal to Kr, I want to get the K's on one side and the concentrations on the other side. So we'll do that by simply dividing both sides by Kr, the reverse, divide both sides by Kr, so you simplify, and then divide both sides by N2O4. We get the following expression. The concentration of our NO2, which is our product, raised to the second power, set over the concentration of N2O4 to the first power, is equal to this ratio of the forward rate constant over the reverse rate constant. This is the very definition of an equilibrium constant. We're going to just simplify to K, Kf over Kr. If the rate law constant for the forward reaction is the rate law constant over the reverse reaction, Kf over Kr defines the term equilibrium constant. It's a ratio that compares the K constant of the forward to the K constant of the reverse. And look how it's calculated. Product over reactant, where coefficients come directly to the power with which it's raised because these are elementary equations. Products over reactants, stoichiometry dependent. Notice it says once equilibrium's reached, the concentrations of those reactants and products no longer change. We mentioned that on the previous slide. There's no net change. This is a flat line of the graph that we just drew together in the margin. This reaction is now in a state of dynamic equilibrium. Dynamic equilibrium is the opposite of static equilibrium. Dynamic equilibrium, things are moving, they're just moving at the same rate. Let's put that into a more general form, known as the law of mass action. We'll make up a general equation, reactant A with its coefficient of small letter a, plus reactant B with its coefficient of small letter b, is in dynamic equilibrium. Notice the double arrows did a little better job there for us, a double arrow, best I could. Creating products C and D with their respective coefficients represented by small letters. When I think about writing out an equilibrium constant, Kc is going to stand for an equilibrium constant that's using molarity for concentration units. The product, C times D, raised to the power of their coefficients, set over the reactants, A and B, raised to the power of their coefficients. Products over reactants, where the coefficients become the order with which they're raised. And I'll stress once more that's fair to do because these are elementary equations. Last chapter, when we were writing rate laws, we had to use initial rate data to determine with which respect these powers were raised, because these were looking at general equations, not guaranteeing you that they were elementary. Dynamic equilibrium, forward and reverse, are always are always elementary reactions, so therefore the stoichiometry becomes with which the power we raise their concentrations. Brackets stand for big M, molar units. Products over reactants, coefficients become the power with which we raise them, and we get this expression called the equilibrium expression. So we call this relationship of products over reactants the equilibrium constant expression. Products over reactants. If I say it enough, hopefully it sticks. Kc is a number. That's it. There's no units to it. It's a number. Kc is a numerical value obtained when we substitute the equilibrium concentrations into the equilibrium constant expression. Plunking in numbers for the values, products over reactants, gets us a number, and that number is called the equilibrium constant. The subscript C does not stand for constant. It stands for molarity units. We'll notice here in a moment we have a Kc for concentration equilibrium, and we'll have a Kp for pressure equilibrium. Kc and Kp are the only two different types of equilibriums that this course will study. Kc is the equilibrium constant using molarity units, C standing for the concentration values in molar units. So the subscript is telling us big M molarity units. We know that it's stoichiometry dependent because these are elementary reactions. So they're part of a larger mechanism. Kc at any given temperature does not depend upon the initial amounts of reactants and products. We see that when we drew that graph, we had a high amount of reactants, they got used up. Products begin to form, and somewhere they'll meet and flatline on our graph. The value of Kc really only depends upon the particular reaction and the temperature with which you're running it. Of course, we know that raising temperature changes K constants from the Arrhenius equation in our last kinetics chapter. Let's just simply practice writing expressions. No numbers in terms of concentration values, but we just want to practice what does the expression look like. We're being asked to write the equilibrium expression for Kc for the following elementary reactions. The first example reads 2 O3s is in equilibrium with 3 O2s. Ozone is O3, molecular oxygen is O2. 2 moles of ozone rearrange to form 3 moles of oxygen. We're being asked to put that into Kc equilibrium expression, where the concentration of molecular oxygen cubed set over the molarity concentration of ozone squared. What might that look like? Take down a guess. We have 2 units of NO with 1 unit of chlorine in dynamic equilibrium with 2 units of NOCl. Think products over reactants. The stoichiometry determines with power with which we raise the orders. Brackets stand for molar units. Take down a guess. How'd you do? In our first example, Kc, I'm using brackets because it asked me to represent the concentration equilibrium. Kc stands for brackets. Those represent molar units, capital M for molarity. We said the molarity of oxygen, molecular oxygen O2, cubed, set over ozone squared. Products over reactants. Stoichiometry becomes the power with which we raise. In your second example, products over reactants, we see the following. The product, NOCl2 squared. Inside of a bracket, NOCl2, because we're using that to represent the molarity of our solution, capital M. Set over the product. Now, product, I just used that. That might have been confusing. Product, I meant that as we're multiplying. When you multiply, you get what's called a product. But I probably should use a better word because on the bottom goes reactants. Products over reactants. And when I said the word product, I meant to multiply the bottom. So hopefully that didn't confuse us too bad. NOCl2 squared set over NO squared Cl raised to the first power. I'm multiplying those two values on the bottom. Products over reactants, stoichiometry dependent. So writing the expression is quite easy. They come from the elementary reactions and just kind of put them in, products over reactants. And here's a nice idea. I know that in our last chapter, the rate law, constant K, we had to work out a little formula to help us derive the units. We said it was 1 minus the overall order per second or per minute, whatever the time was. But now, since we're using a ratio for the equilibrium constant, products over reactants, where equilibrium constant truly is being defined as a ratio of Kf over Kr, forward over reverse, those ratios actually just cancel out. It says, technically, these do have thermodynamic measurements, measured in activities, not necessarily M, concentration units, or atmospheres of pressure. And it's beyond the scope of this course. It's beyond the scope of any master's level course I've ever had. It's just common practice to say there are no units on an equilibrium constant. There are no units on an equilibrium constant. Now, let me clarify. Yes, there's a unit on a rate law constant, kinetics chapter. There is no unit on an equilibrium constant, equilibrium chapter. This is a ratio of forward over reverse. We'll commonly just simplify to say no units. So no units is a good thing. If that's a question I ask you in class, is there a unit on that? You simply say no. K is indeed a constant. It's constant at any temperature. We said temperature affects the rate, but once a dynamic equilibrium is established, it indeed holds constant. So equilibrium simply sets a position for the concentrations. K is a constant. Temperature affects the kinetics, but not the K in equilibrium. I'd like you to prove that to yourself in the following way. First of all, here's our equation for some experimental data. We have 2 units of NO2 forming from 1 unit of N2O4. The reactant here, N2O4, and the product, 2 units of NO2. We ran 4 different trials, varying the initial amounts of the reactant and product. In the first trial, we started with 0 N2O4 and O2 molar of product. Notice there's an equilibrium. Equilibrium constants must be calculated from equilibrium concentrations, not from initial values, but from equilibrium values. The expression Jot this on your paper. What would the expression look like for this reaction? Product over reactant, stoichiometry dependent. We'd see Kc set equal to the value NO2 squared set over N2O4, product over reactant, squaring the product, coefficient of 1 on the reactant. I want you to take a moment with your calculator and solve for Kc for each of these 4 trials. The value of NO2 squared at equilibrium set over the value of N2O4 to the first power at equilibrium. Even though we have varied the initial amounts, what we're starting with, I want you to notice when equilibrium arrives, what happened to the K constant. Pause the video, calculate Kc for every trial, and in your margin note, I want you to write down for me not only the values of Kc for every trial, filling in that blank, write down your observation. How did the initial data affect the equilibrium constant, Kc? Pause the video and start up when ready. I bet you've noticed every trial that you calculated. Trial 1, 0.2113. Trial 2, 0.211. Trial 3, 0.213. Trial 4, again, 0.213. You calculated 4 different trials and came up with the same K constant. K is indeed a constant. Your observation, the initial amounts of reactants and products did not change the equilibrium constant. That the ratios that were established at equilibrium always give me the same constant. Now, emphasis on what I'm trying to say, easy. Never use initial amounts, always use equilibrium amounts when calculating for K values. We've mentioned KCs, standing for concentration molarity units, and I made note, kind of seeding this, that there is another type of K constant for pressures, and that will get a Kp. When the reactants and products are all gases, we can formulate the equilibrium constant expression in terms of partial pressures instead of molar concentrations. Instead of using brackets, which stand for molar units, we use a capital P for pressure and then sub the reactants and products, subscript the reactants and products. If our equation showed A plus B forming D plus E, I don't know why I did that. A plus B makes D plus E. Products over reactants, but using partial pressure denotion. This is what I would read. Kp is equal to the partial pressure of product D raised to the coefficient D times the partial pressure of product E raised to its coefficient E set over the partial pressure of reactant A raised to its coefficient A and the partial pressure of reactant B raised to its coefficient B. The only difference is instead of using brackets, we use a capital P to denote pressure. And in this chapter, as with all equilibrium expressions, we'll always use atmospheres for our pressure unit, ATMs. Standard pressure in an atmosphere is 1. Sometimes if you're given torr, millimeter of mercury, you may find it just convenient to flip that to an atmosphere so that when we calculate from Kc to Kp, we come up with a common answer. Products over reactants, stoichiometry dependent. If we use molarity units, we get something called Kc, and if we use pressure units, we get something called a Kp. So concentrations, Kc, pressures, Kp. For any given reaction, the values, an actual number, the numerical value of Kc is going to be different from the numerical value of Kp's. Remember, pressures only come from gases. Molarity units can either be gases or aqueous ions. So we want to indicate, let the reader know, are you referring to a K that's a concentration or a P for a pressure? We have to be able to look at what kind of K. So notice the denotion in this title, Kp, now I know you mean pressure. Kc, now I know you mean concentrations. So every good K constant should have a P or a C. Although I'll tell you, sometimes I see KEQ, K little subscript EQ to just denote an equilibrium constant, and it's just put in there to use it for a mathematical problem. Wouldn't matter if it's KC or KP. So sometimes in various texts I see KEQ to just let you know it's an equilibrium constant. Ideally, you would let the reader know if that equilibrium constant was being measured with molar units or with atmospheres of pressure. So KEQ, I'm just sharing, I've seen that out there. I think even some of our multiple choice questions will use that general KEQ formula. Well, how are molarity and pressure actually related? And of course that all ties back to that ever popular Pov-Nert equation. That equilibrium measured in molar units and equilibrium measured in pressure units can easily be converted from one into the other form. Kc's into Kp's and vice versa, all tying back to Pov equals Nert. So let's jot down, if PV equals nRT, we know pressure, atmospheres, volume must be in a liter, N stands for moles, R is the gas constant, 0.0821 for the atmospheres of pressure, and Kelvin temperature. Knowing that moles per liter is the very definition of molarity, I'm just going to rewrite Pov equals Nert, showing in this parenthesis N over V. Moles over volume, moles over liter. Really, that's just saying P equals MERT. That sounds familiar from our colligative properties, doesn't it? And knowing that if moles per liter gives us our a bracket, and that's molar units, the pressure for substance A is now written with a bracket RT. The bracket means molar units. The concentration of this substance A in molarity units times R times T. R is 0.0821 and T is the Kelvin temperature. So we just rearranged a little Pov-Nert. And now, looking at that, we have derived the following formula. Write this down big, carefully, circle it, box it, somehow show yourself. When I'm being asked to convert from a Kp to a Kc, or a Kc into a Kp, it's a plug and chug formula using the following. I initially just showed you how I derived it. Kp can be found by taking the Kc, multiplying RT, and raising that R times T product to the delta N. What does that mean? The delta N. Well, delta we know stands for change, and N is the number of moles. Delta N is the change in the number of gaseous moles in the chemical equation, comparing products to reactants. Delta N is simply taking the moles of just gases, emphasize that to yourself, just gaseous product moles from gaseous reactants. Products minus reactant gaseous moles. So it's just a subtraction from the coefficients of those things that are gases. Kc times RT raised to the delta N. Quite easy to use. Delta N, moles of gaseous product minus gaseous reactant. Let's show you one. Let's try one. And I think you flip your page to actually see the problem here. I'll read it for us. It says, in the synthesis of ammonia from its constituent elements, Kc is given as a value of 9.6. Notice no units, just a number, 9.6. And it was recorded at 300 degrees Celsius. If we know the Kc, I'm being asked to calculate the Kp for this reaction at this particular temperature. Well, step one. Let me see on your paper the balanced equation for making ammonia from its elements. Step one, as any good chemist does, they write out their recipe. Gaseous nitrogen reacts with 3 moles of gaseous hydrogen. There's the best thing I can do, a dynamic equilibrium arrow, to form 2 moles of gaseous ammonia. N2 plus 3H2 forms 2NH3. All reactants and products are gases. Now remember, Kc was what was given to us. Kc was given in the problem as 9.60. Alrighty. So we're being asked to change Kc into Kp. Remember our formula. You boxed it, highlighted it, scored it somehow. Kc times RT raised to the delta N. Now let's figure out what delta N is while we're staring at this equation. How many moles of gaseous product do you see? I see 2 in front of the ammonia. How many moles of gaseous reactant do you see? Well, I have 1 from the nitrogen plus 3 more from hydrogen. I'm seeing a total of 4 gaseous moles on the left side of our arrow. Remember, the delta N is products minus reactants for gases only. And I'm looking at a value of 2 minus 4. We get a negative 2. So the delta N, negative 2. Plug it in. We were being asked to solve, just convert a Kc into a Kp, plug and chug. The original value of Kc given was 9.6 times R times T. Now where did the 573 come from? Well, remember the story problem gave us 300 Celsius. I added 273 to turn the Celsius into Kelvin. Now hit it on your calculator. It's the product of R times T raised to the negative 2. RT in a parenthesis raised to the power of negative 2, and then multiply by your 9.6. Remember, there's no units on equilibrium, but what'd you get? Write it down on your paper. When you record your answer for Kp, I found 0.004338. Probably didn't record as many decimals. I got carried away. No units, just a number. It's a very small number. It's giving me an indication that most likely the reactants are being favored in this equilibrium. And we'll talk more about the number itself. The magnitude of the number is what's interesting to a chemist, not so much what it is, but the size it comes out to be. Let's try another. I'll read it with you. For the equilibrium of sulfur trioxide decomposing into sulfur dioxide and oxygen, the Kc is 4.08 times 10 to the negative third power at 1,000 Kelvin units. What's the Kp? Begin by writing out your balanced chemical equation. Turn these words into a balanced equation, jotting down the value for Kc. I hope you pause when needed. Don't cheat yourself from the practice. Pausing and stopping is always a good practice with the video lessons. But I bet we match. I bet you wrote down 2 moles of sulfur trioxide in the gaseous form in dynamic equilibrium with 2 moles of sulfur dioxide and a mole of oxygen. And I put back in our equation how to convert from Kc into Kp, knowing we take the original Kc from our story problem, take the product of R times T and raise that to the delta N. Delta N is products minus reactants for gaseous moles. Kp that was given, the Kc from the story problem, Kp is what we're calculating for. 4.08 times 10 to the negative third power. The R constant to match atmospheres. August 21st is how I remember this number for whatever reason. 0821. The Kelvin temperature is 1,000. R times T raised to the 3 minus 2, that's product gas minus reactant gas. I see 3 minus 2, so raised to the first power. Hit that. Pause the video, hit it, and see what you get. I'd like to know that I don't have a calculator mistake. See if you get the same answer. How about something close to 0.335? Kc converted to Kp. We'll stop the video lesson here for section 1 and 2. Section 1 and 2 of chapter 15 completes this lesson. We're still not yet ready to tackle lesson number 1. We need more in the note pack before we're ready to do that. Lessons for section 3 and 4 are found on the next video.